Hello, everyone. My name is Dabir Kafri, and I'm a physicist in the modeling team here at Quantum AI. Today, I'd like to talk to you about some of our efforts we've taken to do comprehensive simulations of our error correction experiments. So, there are two big things that I want people to take away from this presentation. The first is that when we're simulating our devices, the details really do matter. By details, I mean the details of the noise. An example of this is a simulation we conducted of a previous experiment from this publication that itself was a quantum simulation of the Fermi-Hubbard model with four interacting fermions. So we simulated the actual experiment itself using both a depolarizing channel model, which is more or less agnostic to the physics of the errors in our gates. All that goes into that model is gate fidelities. We also simulated it using a more physical approximate model that matches the observed qubit decay rates, the dephasing times, and readout errors, etc. Right. So in both cases, the predicted average gate fidelities are the same, but when you look at some of the resulting statistics, there is an observed discrepancy. So here I have a figure representing the L1 distance between the measurement statistics, the single qubit measurement statistics for the experiment and for the simulation. And you see that there is quite a noticeable discrepancy between the noise agnostic model and the noise specific model. Now, we see very similar results when we simulate our surface code experiment. So here are some simulation results from our latest surface code scaling experiments. In this first figure, we have a plot of the logical error probability as a function of the number of error correction rounds. This is both for distance 3 and distance 5. The solid lines are fits, and the dashed lines actually correspond to simulation predictions. These are not fits. They come from low-level characterization of errors in the device. And so the Pali Plus simulation that was used to carry out the simulation included things like leakage and crosstalk errors that can lead to long-time correlated errors and also to errors acting on more than 2 qubits, right? And you can see the big discrepancy between this more sophisticated noise model and a simplified Pauli model if you look at, for example, the statistics of detection events. So importantly, the unexplained detection events, those that don't correspond to or would not be predicted by a simple 1 or 2 qubit gate local errors, are not present at all in a simple Pauli model. Also not shown here is the logical error probability coming from the Pauli model, but it is significantly lower as well. So I've motivated the fact that including physical detail is actually quite important when we want to predict how a given experiment is going to run. The other big important takeaway that I want people to have from this talk, though, is that including these details is actually quite hard. And there are actually a couple of reasons that I'll discuss for why it's hard. The first is that quantum computing is hard. And so there are a lot of ways for things to go wrong. There are a lot of details to really include. And so the approach we have to take to account for this is we have to be practical. We have to just include just enough detail to accurately predict what we want to see in the device. All right, so how do we do this? Well, we start with a picture of the experiment using quantum circuits, right? So an ideal circuit would be composed of just a sequence of ideal unitaries and measurements and reset operations on our qubits, right? And this could be described by just applying unitary operations to a quantum state vector. When we want to include noise, we would need to then take this ideal representation of the circuit and map it to a noisy representation, which typically corresponds to having the same original operations, but also appending other operations that represent different error mechanisms. So these error operations are represented using quantum channels, which themselves are numerically represented using these things called cross operators that are the analogs of unitary operators. Usually, quantum channels are applied to density matrices in this way. They represent the fact that our system is typically not a closed system, that it interacts with an environment. One important interpretation that I'll allude to later about these cross operators is that of a positive operator valued measure. You can really think of these cross operators as affecting a POVM, where the probability of sampling one of these POVM results is just given by the standard Born rule. Importantly, because this represents an interaction with the environment, in many of the cases here, these quantum channels do not produce results that are given to the experimentalist. Okay, so now we've shown you how we represent the noisy evolution of the system. How do we actually do a simulation of that representation? So, as I mentioned, typically with quantum channels, we represent them as acting on density matrices, but this will quickly make a quantum simulation prohibitively expensive. So instead, what we're going to do is we're going to use a different approach called Monte Carlo or quantum trajectories, which is based on only maintaining a copy of a single state vector instead of a density matrix. So while this produces less information in a single shot than a density matrix simulation, it's much more efficient. It's quadratically more efficient to do, and it still faithfully samples from the statistics of the noisy circuit. How does it work? Well, basically, you start with a pure state vector, and then whenever you apply each of these channels or unitary operations, instead of applying all of the cross operators at once, you sample a single cross operator using the Born rule, and then you apply that just a single cross operator from the channel to your state vector and normalize. And then you follow this step by step through every quantum channel. And by the end, you have a record of all the cross operators that were sampled. The ones that actually corresponded to measurements are then what the experimentalist would see. So again, I'm going to stress that this is we're really kind of mimicking what an experimental implementation would give you. And so we're trading off detail for the ability to consider much larger system sizes, because again, these are vectors and not matrices. Okay, I've described how we represent our noisy circuits with cross operators. I described how we do a quantum simulation. The last detail that we need to think about is like, where do we get these cross operators from? And I want to point out that this is actually a lot of work, because again, quantum computing is hard. There are a lot of error mechanisms. Here I've listed some of the dominant error mechanisms in superconducting qubits that we've identified in our systems. And I want to stress here that the work required to include all these errors in our simulations is non-trivial, right? So you might start with a theorist like Andre, who wants to model the effect of error mechanism X. So he comes up with an efficient description of that will eventually produce cross operators. And then experimentalists like Kevin will then conduct experiments to actually test the predictions of this model. And finally, we will have someone like me who implements that model numerically in an efficient way to then test the validity of to compare the experimental results to the analytical predictions. Now, this is a lot of work, and I want to touch upon why we need to do this, why this is important to do for our quantum computing efforts. Why do we care, right? The reason we care is because without being able to faithfully predict how a device is going to behave, even a small scale device or not necessarily, or the larger scale logical memory, it's going to be impossible for us to actually scale up or engineer a device that works, because we won't know things like what component errors for each operation we need, for example, or how we should design the circuit to minimize the total logical error in the fault-tolerant device. I'm reminded of a quote from Google's Site Reliability Engineering Handbook, which is that hope is not a strategy. We can't just hope that this will work. We really have to predict that it should work before we try to build it. Let me give a quick summary of how we can kind of put all this together for the quantum simulation. Google has spent a lot of time developing both open source and internal libraries for doing the work that I've just described. So on the level of quantum circuits, there's the circ library that can represent efficiently these operations, and also has some logic in it baked in to add these noise to the circuits. Once we have the noisy representation of the circuit, circ then ties into several quantum simulators, including QSIM, which allows us to actually do the quantum trajectory simulation, or optionally other kinds of simulations as well. I want to stress that this is also the combined effort of multiple physicists, multiple computer scientists, and multiple software engineers. Okay, so there's another question that comes up, which is, sure, we can do a faithful quantum simulation of a device, but we're going to have, in principle, in the future, 1,000 or million qubit devices, right? And so how are we ever going to possibly simulate that, right? This is the other reason why these details are hard, because they are very, very expensive to simulate. And so the approach we have to take here to solve this problem is the typical approach of a physicist, which is just to make approximations. We have to make some approximations in order to be able to describe a large-scale device. How are we going to do this? It's going to be a trade-off between model detail and scalability, right? So currently, we have our quantum simulations that are nominally exact, that they can describe current device sizes at an exponential cost. What we're going to have to do then is take our exact noise models, our exact description, and do some kind of approximation on top of this that leads to a simulation that is classically efficient. Ideally, the simulation cost will actually be linear in the number of qubits. So our goal will be to be able to simulate a 1,000 qubit device or a million qubit device. I will specify here that this is not to say that our goal is to be able to simulate an arbitrary quantum system of arbitrary size efficiently. That is not possible. Our goal will be to only be able to simulate to start with only just a single logical memory. And the way we can do this is by taking advantage of the structure of these error correction circuits. So it turns out that the way these circuits are implemented is the operations that are applied are only a subset of all possible operations, right? The unitary operations themselves are called Clifford unitaries. And that means that we can actually have a very concise description of our quantum state using something called stabilizer states, which in practice means that these are states with very, very many good quantum numbers. When we apply any of these Clifford operations or measurements or resets to our stabilizer states, it turns out that all this does for you is it maps you from one stabilizer state to another stabilizer state. And so you never need exponential resources to do the simulation, right? The trade-off is that this cannot simulate all possible quantum physics. For example, if we are simulating the noisy evolution with arbitrary Krauss operators, we will lose this structure, and we cannot simulate this system without requiring exponential resources. So the way we solve this is, again, we have to make some kind of approximation. We take these noisy channels with arbitrary Krauss operators, and we convert them into other noisy channels whose structure preserves the original structure of the circuit. So right now, what we're doing to do this is doing something called the Pauli-Twirling approximation, or generalizations of the Pauli-Twirling approximation. To motivate this, I'm going to look at a single qubit case. So here I have a quantum channel acting on a single qubit with arbitrary Krauss operators. And I want to get out of this another quantum channel whose Krauss operators are proportional to Pauli operators. And because they're proportional to Pauli operators, which are a subset of the Clifford group, applying this Pauli channel to our system will still preserve this nice stabilizer structure. So how do we go from here to here? Well, you can really think of doing this in the following way. You prepare a maximally entangled state, you apply your noise channel to one of the qubits, and then you measure the XX and ZZ stabilizers. These are commuting observable, so we can measure them simultaneously. And by looking at the statistics of these measurement outcomes, we can actually infer effectively what the probability of an X error here would be, or a Y error, or a Z error. So for example, if an X error happened, it would cause the ZZ stabilizer to flip. Or if a Y error happened, it would cause both of these stabilizers to flip. So from these measurement statistics, we can infer the corresponding probabilities that the same Pauli channel would have predicted. I will also stress here that this kind of approximation, this effective approximation, will produce a quantum channel with the same fidelity. This kind of description is also nice because it lets us directly generalize to devices, or to error channels acting on more qubits, and also to error channels acting allowing us to account for leakage outside the computational subspace. All right, so let me go over some simulations we've done to try to validate this approximation. Here I have the results of a simulation of our distance 3 surface code experiment. We've taken, for each one of these points, this corresponds to about 200,000 samples. Here I'm comparing the quantum simulation with the Pauli plus simulation. Here the Pauli plus is the result of doing this kind of approximation that also accounts for leakage and lets us include things like multi-qubit crosstalk as well. So you see that there's actually a surprising amount of agreement between the quantum simulation and the classical simulation, both in the detection event fractions, the detection event statistics, and here in the logical error probabilities that are observed. So here the two curves correspond to the Z basis and X basis experiment. This is actually, the amount of agreement is actually quite surprising. In other results in the literature, there wasn't this much agreement. I think we can explain this in multiple ways. Like one, I think, important explanation is that most of the errors that we're including are incoherent errors. And this is a result of the fact that the experiment itself is carefully designed to mitigate coherent errors. The main concern about coherent errors is that a coherent errors, when applied in sequence, can add up coherently instead of classically, right? And so if you did a twirling approximation on these coherent errors, you will make a different prediction about what error should be observed. But in our case, most of our errors are incoherent, and so we don't really see this, right? Additionally, it's known that the act of measuring the stabilizers themselves in this experiment effectively has an effect of effectively twirling a lot of noise itself already. Finally, I will also say that the caveat here is we're only looking at distance 3, and we are near the error correction threshold. So it's believed that in this regime, we don't expect to see a huge difference in predictive quality between a classical approximation, or specifically the twirling approximation, and a brute force quantum simulation. So I will say that, yeah, more work needs to be done to come up with classical efficient approximations that still allow us to capture the errors in the regimes where we have larger distance system sizes, or once we're in the fault-tolerant error regime. But this is a good first step, I would say. So let me conclude with a summary of my presentation. So first, simulating a quantum memory or an error correction experiment is very hard because quantum computing is hard. So there's a lot of model complexity to account for, and there's also the computational complexity of the simulations is quite challenging. Furthermore, this is still a necessary thing that we're going to have to do in order to be able to get to a fault-tolerant quantum device. And it's an ongoing effort requiring inputs from multiple people. So physicists, computer scientists, software engineers, electrical engineers, etc. There's a lot of work being done here, and there's still a lot of interesting work to be done. So with that, I'd like to conclude, and if there's any time for questions, I'll answer some questions. Thank you.